In this short video today, we're going to look at some trends on the periodic table and explanations for them now that we know something about the structure of the atom. One trend that we see is that of atomic radius. In general, atomic radius decreases as you go from left to right across a period. This is explained by something called effective nuclear charge. The effective nuclear charge is a combination of the effects of the nuclear charge, the actual charge in the nucleus, which we model by Z, and the effect of some shielding electrons. Now these are the inner electrons from the inner shells that sort of take up the pulling capacity or the attractive capacity of the nucleus. So you have a nucleus that has a certain number of protons, and that's what Z is, it's its charge. Take away all the inner electrons and you have what's called the effective nuclear charge, Z effective. Now the bigger the effective nuclear charge is, the more strongly the outside electrons are going to be pulled toward the nucleus, and the smaller that atom's going to get. We can see this using a couple of examples. Let's take two elements that are in the same period, sodium and chlorine. Sodium's electron configuration notation is 1s2, 2s2, 2p6, 3s1. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. Now the shielding electrons, the ones that are in the interior, are the 1s2, 2s2, 2p6 electrons. And that's the same for both of these things. So S in our Z effective calculation is going to be, in both cases, 6 plus 2 plus 2, which is 10. Now, the effective nuclear charge is made up of the nuclear charge minus those shielding electrons. Well, sodium has got 11 protons, so its effective nuclear charge is 1. Chlorine has got 17 protons, so its effective nuclear charge is 7. Because chlorine has a bigger effective nuclear charge, its pull on the outside electrons is bigger than sodium's is, and so chlorine will tend to be a smaller atom. We can see this trend on this chart here. You may have seen this before. In fact, you may have created one of these in a previous chemistry class. If we look at what's going on with the atomic radii, we can see that when we come to the beginning of a row, like here's lithium for example, we see a decrease as we go across that row in general until we get to the beginning of the next row. So this is lithium, which is element number 3, and then 4, 5, 6, 7, 8, 9, 10, 11. Here's sodium, number 11. 12, 13, 14, 15, 16, 17, 18, 19. Well, that's potassium. And then we see that same trend repeating itself, and rubidium is going to see the next big spike. So atomic radius gets big at the beginning of a row, and then we go across to the right and it decreases in size. Atomic radius increases from top to bottom, and that has to do with the fact that you just have a higher outer shell. A bigger orbital contains those outer electrons if you're lower down in the period. So let's do another comparison. Here's sodium. It's 1s2, 2s2, 2p6, 3s1. But in the same group, we have potassium. Potassium is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. The outside electron in sodium is in a 3s subshell, and that's just smaller than a 4s subshell, and so potassium is going to be bigger than sodium will be. Their effective nuclear charge is essentially the same because it's 1 greater than the number of shielding electrons. We can see these trends illustrated in this three-dimensional graph here. This is like a mirror image of upside down periodic table in a way. Just to orient you, this is group number 1, so this is hydrogen here, and this is group number 8, so this is helium right here. Now, as we go across a group from hydrogen to helium, so this is actually from left to right on a real periodic table, we see a decrease in the size of the atom. Following these bars across, you can see clearly there's a decrease as we go from left to right, which is right to left in this thing because it's mirror imaged. And then as you go down a group, which means you're going this way from period 1 through period 6, you see an increase in size. Hydrogen, lithium, sodium, potassium, and so on. Ionic radius follows a trend pattern that parallels that for atomic radii. So as you go left to right, they get smaller. As you go top to bottom, they get larger. But cations are smaller than the atom. And this is because as you remove electrons, the net positive charge in the atom gets larger and larger. And so the outer electrons are pulled even more tightly than they were before. And often when you form an ion, you are evacuating electrons from the highest shell. And so the new highest shell is now a lower shell, and its electrons are farther in, closer to the nucleus. Anions, on the other hand, are larger than the atom. And this is because you have the same effective nuclear charge. Effective nuclear charge stays the same because when you add electrons to an atom to make it an anion, you are not putting them in the inner shells. So the number of protons and the number of shielding electrons is still the same. However, what happens is you now have more outer electrons. And with more outer electrons pulled by the same effective nuclear charge, that pull for those outer electrons sort of gets diluted because there are more of them, and each one is pulled in not quite as much as it used to be. And so the atom expands in size. Ionization energy is another thing that shows trends in the periodic table. First of all, let's define ionization energy by looking at the first ionization energy. The first ionization energy is that how much energy it takes to convert an atom from a neutral atom to a 1+ ion. So for example, if I have a sodium atom and I convert it to a sodium ion by removing one electron, the delta H for this process is going to be the ionization energy, the first ionization energy, because I've removed the first electron from that atom. So what happens if you're going to ionize an atom? Here's an atom, and the nucleus is there, and here's the electron that you're trying to take away. You want to remove this thing from the atom if you're going to ionize it. What does that mean? Well, you have to break up the attraction that exists between the nucleus and the electron. What is that attraction like? Well, it's an electrostatic attraction. An electrostatic force is proportional to the charge on the first particle that's being attracted times the charge on the second particle divided by the square of the distance between the two particles. Now in an atom, electrostatic force is going to be proportional to the charge on one particle is the nucleus, and so that's the effective nuclear charge, times the charge on the second particle. Well, that's the charge on one electron, divided by the square of the distance between them. Well, the distance between them is just the radius of the atom. So let's see how that plays out in periodic trends. In general, first ionization energy increases from left to right, and that's for two reasons. Remember, the ionization energy is going to be proportional to the effective nuclear charge times the charge on an electron divided by the square of the radius of the atom. As you go from left to right in a period, the effective nuclear charge is getting larger, and since that's in the numerator, that means the ionization energy will get larger as you go from left to right. And the radius is getting smaller, and since that's in the denominator, that would also cause the ionization energy to increase. So ionization energy gets larger as you go from left to right in a period. We can see that trend in this chart. Here's element number 1, so here's helium right there. In its group, helium has the highest ionization energy. And then when we get to the start of a row, it drops way down. There's lithium, number 3, and then we go 4, 5, 6, 7, 8, 9, 10. And there's neon way up there. Neon has a very high ionization energy because it's got the highest effective nuclear charge and the smallest radius. And then it drops down and gradually climbs, and you get to the next noble gas. So each one of these spikes represents a noble gas. First ionization energy decreases from top to bottom. Now let's see why that would be. Remember, ionization energy is proportional to the effective nuclear charge times the charge on an electron divided by the square of the radius. What's happening here is as you go from top to bottom, the radius is increasing because the shells are getting bigger. The effective nuclear charge is going to be the same as long as you're in the same group. So the only factor that influences anything is the increasing radius. Since that's in the denominator, that means a decrease in ionization energy. You can also see that trend here. looking at the noble gases for an example, here's helium, neon, argon, krypton, xenon, and radon is way down here. Well, we can see that as we go down that group of noble gases, there's a decrease in ionization energy. We can see that in this two-dimensional graph as well. This is laid out differently than the last one that you saw. This is actually looks just like the periodic table. Here's hydrogen right there for reference, and here's helium. As I go across a period, pick any period, I see an increase in the height of the bars. As I go down the group, I see a decrease in the height of the bars. After the first ionization takes place, then we have these successive ionizations, the second one, the third one, as you remove more and more electrons from the atom. Successive ionization energies are higher than the first ionization energy, and that's because as you remove more and more electrons, the net charge in the atom becomes more and more positive, and that pulls the electrons in more tightly and makes it harder to remove successive electrons. And then another thing that happens is after the electrons are moved from the highest energy level, the highest shell, and then you try and remove that first one from a lower shell, it becomes dramatically more difficult. You can see how dramatic this is if we use an example. Magnesium is 1s2, 2s2, 2p6, 3s2. That's a neutral magnesium atom. We're going to ionize this to magnesium 1+, and that electron is going to be lost from the highest shell, which is the 3s subshell. So it becomes 1s2, 2s2, 2p6, 3s1 after ionizing. The amount of energy that takes is you have to input 738 kilojoules for every mole. Well, now we're going to ionize from Mg plus to Mg2+. And Mg+, remember, is 1s2, 2s2, 2p6, 3s1. The electron is going to be removed from the highest shell because that's the one that's farthest out. It's easiest to take away. So that means we end up with 1s2, 2s2, 2p6 because that 3s sublevel is now not occupied at all. Delta H for that process is just about double, 1415 kilojoules per mole. Now we're going to take that Mg2+ and ionize it to Mg3+. So now we're going from 1s2, 2s2, 2p6 to 1s2, 2s2, 2p5. So we're removing an electron from what used to be an inner shell. It's now much closer, that electron, to the nucleus than the 3s electrons were, and it takes a lot more energy. We can see that delta H for this process is 7,731 kilojoules per mole. Much, much more energy is needed to remove that third electron than the previous two electrons combined. So that explains why Mg2+, we see that all the time as an ion. Mg3+ is unheard of. This just doesn't happen. It takes too much energy. We can see the ionization energy trends on this three-dimensional graph. So this shows only the second period. So this is lithium through fluorine. This is the left-hand side of the chart. This is the right-hand side of the chart. So it's like you're looking at the chart from above. So we can see the trend in first ionization energy. This is the first ionization energy right here. Lithium is lowest, and as you go across the period, it gets higher and higher. But now this isn't groups going down these columns. These aren't successive periods. These are successive ionizations. So for lithium, you ionize it once, and then you see this dramatic jump up to that second maroon bar. Well, lithium makes a 1+ ion. That's why. Beryllium, there's a small jump from blue to maroon, a huge jump from maroon to yellow, and the yellow is the third ionization. So that's why beryllium makes a 2+ ion, but it doesn't make a 3+ ion. Here's boron. Small jump to maroon, small jump to yellow, huge jump to green, which is the fourth ionization. So boron makes a 3+ ion, but it doesn't make a 4+ ion. And you can see that wherever that large column is, that's where the ionization is likely to stop. Now, we know that carbon doesn't really ionize to 4+ very often, so when you start getting to a jump that's much bigger than that one, well, it's just too much energy for ionization to occur in the first place. One last trend that we're going to look at, that's electron affinity. Electron affinity is the attraction that an atom has for electrons that are out there loose, waiting to be absorbed, electrons that come from somewhere else. Electron affinity is greatest for small, highly nonmetallic atoms. So if you think about a periodic table, just drawing a real rough sketch of a periodic table, here's fluorine up here. Forget about the noble gases because they're not doing anything chemically. Smallest is farther up here, smallest is farther over here, and the nonmetals are up in that corner, and that is the general rule. The farther up you are in that corner towards fluorine, the greater will be your affinity for electrons. Electron affinity can actually be measured, and it turns out to be negative numbers because you're actually releasing energy when you allow electrons to move into an atom. The less negative it is, the lower is its affinity for electrons.